If I do like this and like this, all right, so again, we are, to make sure that everybody is on the same page, we looked last week, at the Langevin equation. We said that this is x dot dot plus gamma x dot. So there can be a force plus a force, but we didn't look at this with the force. And then we said that there was a coefficient which is 2 epsilon gamma square root w dot, where W is Brownian motion. Thanks. W is Brownian motion. Continuous time Brownian motion. Epsilon and gamma are constant. This is usually in physics, this is called the energy. This is in kT, for example. And this is gamma, this was the viscosity. Okay. And so last week, we said, we looked at the case where F was equal to 0, and we derived this equation from consideration, saying that you have a single particle. We have a particle, x of t, that moves in a medium where the ball is getting reflection. And this is why, this is due to this reflection, that you get here the Brownian noise. And this is due to an assumption that the drag force is linear. Otherwise, you see, you know that in airplanes, when they go fast enough in some hydrodynamics at very high speed, it's not anymore linear. Because this is an assumption, this is a phenomenological. You know, it can be gamma, this can be to a certain power of the velocity. This is how people have modeled supersonic things in fluid. But this is not our goal here. This is to see where answers assumptions, or the physical assumptions, the modeling, versus derivation. Okay? So this is where we got last week. So wait, where did we say? Yeah. So and then we didn't say what happened for gamma large, right? So for example, have we said that for gamma large, let's say when gamma goes to infinity, large enough, compared to you know, any relevant scale, when gamma goes to infinity, this equation converges in the sense that the probability density function converges to what is called the Smoluchowski limit of the Langevin equation. That is, when gamma is infinity, goes to infinity, is large, then this equation converges in terms of the probability density converges, except for extremely short time, to gamma x dot plus f equal 2 epsilon gamma w dot d. We haven't said this, right? That when gamma goes to infinity, let's say equation, let's say 1 gamma, equation 1 gamma converges. This means of convergence. So this is in probability convergence to this stochastic equation. We haven't seen that yet. Okay, so I'll show you how it goes, why you have this, and what is the limit of this. Because you can find the limit of this for short time. For short time scale, and this is important when people are describing chemical reactions. Chemical reactions for very short time of binding, you have the limit of the Smoluchowski equation. Because this is not correct, this approximation. We will see where it comes from. It comes when we have the expression of the probability density function of the diffusion. You will see it's clear where it comes from, but now I'll mention it. So this converges for t in the interval t bigger than a capital T, let's say, t0. And this t has to do with basically is 1 over the friction coefficient. This should be 1 over time, no? Yeah. So this is the time. Below, after the, you can do this after this time. Below this time, no, it's incorrect. You have to go back to the full equation. Okay. All right, so let's discuss this. So why am I switching? Or maybe, okay. So maybe there are a few remarks. Few remarks before we go into this. So this is what I just said at the beginning. So previously, an assumption, one assumption of the derivation is the linearity of the friction force. That is, F was minus gamma velocity. So this is a linear approximation, linear approximation. Now, instead of this, you can have what we call a time kernel, a kernel that accounts for the history. And so, for example, this is the diffusion in a crystal, for example. Diffusion in a crystal is actually modeled with different properties that I will write now, the Langevin equation, which is the acceleration plus the integral from 0 to t of phi of s, and then you have to integrate over all the path of the velocity ds, and there can be possibly a potential, and psi of t if the fluctuation is the noise term. And this satisfies the correlation, which is the expectation of any 2 time ti tj for any 2 times. So psi is this is the noise, is gamma. Gamma is the viscosity, that the energy cavity phi of any of these 2 time ti minus tj. So for any 2 time ti tj. And so I'm getting hot. And so in a crystal, phi of s, this has been found empirically. Phi of t is sine omega t divided by omega t. Okay, so what are we discussing here? We said that a different model. So what is a crystal? You know, a crystal is a periodic organization of atoms with a certain structure. And now you're interested of the Brownian motion of a particle inside this structure. How do you describe this? It turned out, after years of work, that the description is not something where you just look at the velocity at one point. You have to take the path from 0 to the point t with a certain kernel. But if you do that, and if you want to respect fluctuation dissipation, you need to have this relationship, which I'm not going to prove here. It's going to be, it will take me another 2 hours. That there is the connection, that the same that you have here, square root of gamma and gamma. This is the connection that you need to respect. This is, again, I'm not describing this. I'm just showing to you that there's a different type of models that can be used for different application. For example, Yeah, it is. It is. Because you respect, you have here the your trajectory x of t. I mean, if you're in dimension 2 and dimension f, you have your all steps, your all variables, and it satisfies a stochastic equation. Now, what you can have from this is, for example, you know what is the colored noise? The colored noise is a noise passed through a low-pass filter. A colored noise, instead of, so how you build a colored noise, basically, you have a noise which is minus alpha u plus, let's say, beta w dot. This is Brownian motion. This is a w dot that is here. And here you are killing the high frequency. Right? You know what is a low-pass filter? Oh, okay, so just, you know, you don't care about the name of this. This is the solution, so U is called a colored noise when it is solution of this equation. You generate, how you generate such a noise? You just use this stochastic equation. And again, this is, so you can now imagine a particle moving with this type of noise. So there are different possibilities for the noise, and different possibilities for the linear term here, which would represent here the history, because you integrate from 0 to time t. Okay, so this is, those are simply, yeah, and so I have to tell you, because there is a huge literature on this, what is called anomalous diffusion. You will find a lot in the literature. Anomalous diffusion is the case where phi of t, well, it's not very well written, but anyhow, phi of, well, okay, phi of t is t minus s or s minus t to power alpha. It should depend really on t and s, right? So this is true only for s between 0 and t. So that you take this and you put it in here. All right? And when you look in the literature about the anomalous diffusion, this corresponds to solving this equation using this type of memory with this particular kernel. This is called a kernel. And there is an industry of trying to understand what are the properties of the trajectories that satisfy this condition, that have this type of memory kernel. Okay? All right, so this is the remarks. So now I'm closing the remarks. So this was the remarks. And now we are going to this friction approximation. So Smolachowski approximation. So for understand this, let me remind you that we had V dot plus gamma V equals F, right? Yeah. And then we had X dot, which was the velocity. So in the class last week, yes?
For the anomalous diffusion, if you look at the correlation of the psi TA and psi Tj, and if you take the phi you wrote below,
yes,
you mean that the second moment would diverge?
Sometimes, yeah, there is no second moment. Of it depends on the your process.
What does it mean physically that the second moment diverge?
I don't know. I mean, physically, what do you mean physically in terms of, for example, in classical diffusion, when you look at mean first passage time outside the domain, there is no mean first passage time because this moment diverges. Okay, suppose you look, you are interested in how long it takes for a particle to enter here in this domain. So the time it takes is the time when you average over all the trajectories like this, which can go to infinity. So this is an example where the first moment, the second moment of the time, that goes to infinity. So now what is the meaning of this? It's very hard to, you need to have a specific physical settings to understand what's the consequence for the physics. I mean, mathematically it diverges. Now you're asking what's the consequence? It depends on the question you are asking. For example, here, if you do mean first passage time even for Brownian motion, if you're outside the domain, the time and the square of the time is infinite. All the moments are infinite because of the situation you are looking at. If you do this inside, they're all finite. So there is no absolute answer to your question. I'm saying it depends on the situation that you want to characterize. I think this is what I can say. But there is an entire literature. I mean, people have looked at properties like mean square displacement to some power, or look at how it behaves for delta t small. So then, you know, you have some formal calculation. For example, it's very hard to do something with the give a solution to the that's what we are going to say, the Fokker-Planck equation, which is the probability to find the particle for an anomalous diffusion, or what is, for example, the mean first passage time. Everything is through the mathematics that you can answer some of the question you're interested in. Okay, so now let's go back to this. I wanted to integrate this equation twice. So you agree that x of t, if you integrate v, so what we have seen last time we saw that v of s is v0 exponential minus gamma s plus the integral from 0 to s of exponential gamma u minus s f of u du, correct? And now I want to integrate this one more time to get x. So for this, you just, you know, formally integrate this. So this is x0 plus v0, and if we integrate, this will be 1 minus gamma. So this is now t divided by gamma, right? Plus the integral from 0 to t of the integral from 0 to s of exponential minus gamma u minus s f of u du ds. You agree? I just, you know, integrate everything. I did nothing else. And now if you change the order of integration, instead of integrating first u and then s, you just reverse, and you get here the kernel that appears. So you'll do it at home. This is integral from 0 to t of 1 minus gamma of u minus t divided by gamma fu du. And now if I put everything here on the left side, I get x of t minus x0 minus v0 1 minus exponential gamma t divided by gamma equals, right? I just put everything here in the left-hand side, and the only thing I haven't documented exactly is how you reverse here the integral. But this is not hard. You're right, you're integrating over a triangle like this, and then you do it like this. All right? So this is what you get. And now, so f of u, we said last time, this is the Brownian motion. And now we integrate a deterministic function over Brownian motion. So what is this? This is, so this, which is equal to this, which means that this is Brownian motion, and then we just have to change the time or get the variance. I mean, how you characterize this quantity? What is the mean of this? If you average, this is 0 because f of u is correspond to a Brownian motion. And now the only way to characterize it, I mean, fully, is to calculate the second moment, which means that this entire thing here is a Brownian variable with a moment, a second moment that we have to calculate. Now, how do we do this? So, okay, let's just write down what you guys said. So, if you call this is now our kernel, g of u, let's say minus t. So, this j of u minus t, f of u, the expectation, integration from 0 to t, the expectation of all of this by definition, because this is a Brownian motion, and this is deterministic. So this is the integral. Okay, let me write it once. This is j of u minus t, expectation of f of u, which is Brownian motion, which is 0. Okay, and now we are left with the second moment. So, you know, we already did it, so I'll go. So this is the expectation of the integral of 0 to t of g of u f of u du squared. So how do you calculate this? We did it several times. Either you decompose in a sum, or you want me to do it one more time, just to practice? Yeah? Okay. All right. So this is j. For example, you can you can look at this as an approximation by the sum of g k delta t f of k delta t multiplied by delta t multiplied by j of q delta t. You know, something squared, this is squared, this is twice the same. So I'll sum over k and over q. This is something, you know, that goes square. So this is j q delta t f q delta t multiplied by delta t, and we have to get some, and that's it. And we have to take the expectation of all of this. So everything will be 0 except when k equals to q. And so we are going to be left with the classical thing, which is g squared k delta t. And those are the Brownian increments. So we are getting then the this is d omega k. This is the expectation of d omega k squared, right? Because when k is different of q, this is 0. So we are left with something with only k. And by definition, this is exactly delta t. And so basically, we are back to the integral because, again, I'm not going to detail this. You cut, and then you go to the limit where the delta t goes to 0. So this is a Riemann sum. When delta t goes to 0, it converges to now the classical integral, which is gq of s ds. All right, and now what is the result? So this is this function squared, right? And where did I? Okay, I see. And also I forgot something. No. Yes. F. What was in the note? The expectation of f squared from last week. Expectation of delta q, delta k squared. You have it? This was 2q or 2 alpha or 2 gamma, no? You don't have the notes of last week? 2D. 2D? or 2q, I forgot how it was, how I wrote it.
2q delta t.
2q delta t, okay. 2q delta t, so here, this is not delta t, but there is a 2q multiplied by 2q, all right. So now this is 2q, yeah, okay. Is it correct? Is it correct? Okay. Okay, so now what is this? You have to integrate twice, you have to integrate 1 minus exponential minus gamma t. So this is squared minus 2 exponential minus gamma t divided by gamma squared. And we have to integrate this from 0 to t, whatever, no, sorry, from 0 to s. Yes, from 0 to s. And this is ds. This is 2q divided by gamma squared. So what do we get? Just integrating 1 from 0 to t, it gives you t. Minus, so there is a 2. I'll start with this one. Is correct? Okay. Minus 2 exponential gamma of u minus t. Why do I get this here? Yeah, maybe. Yeah, so this was. Yeah, this is u minus t, right? So this is u minus t, so I have to integrate with respect to u, and I have a t. So this should be exponential of minus gamma of u of s minus t. And this is of s minus t. All right. So t is fixed, and you integrate with respect to s. Somebody is checking, right? My calculation. You don't rely on me. So this should be minus 2 exponential minus gamma t, exponential gamma t minus 1. You should redo them. Plus exponential minus 2 gamma t, exponential 2 gamma t minus 1 divided by gamma squared. Is it what you get? All right, so what did I do? You just calculate this quantity. Yeah, you just calculate. So this is, you have to calculate this squared. Yeah, this is what we're calculating now. So j of s, this is j of u of minus t. So this is, you replace u by s, you put it squared, you integrate. So it should not be hard.
There should be a plus in the middle.
A plus?
1 plus.
That's right. Minus, this is this one. Okay. Gamma t, then minus gamma s. I'm not sure this is correct, but I hope this.
Last one is 2 gamma and not gamma square. Yeah.
Here?
Yeah, 2 gamma, I would say.
Good. Yes, correct. Okay, now this is quite interesting because this is the variance of this quantity. So now we are ready to write what is the probability of our process x of t minus x0 minus v0. I mean, you could, well, okay, I write it this way, minus gamma t divided by gamma. Condition that, yeah, okay, this is clear that there is no conditioning because for t equals 0, x of t equals 0, and the derivative is v0, right, from this. So what is this? This is now a Gaussian of variance sigma t. So let's suppose we're in dimension 1 or 2 or 3. It's an important, so I'll put, let's say, dimension, okay, I'll do dimension 1. So it's 1/2 exponential of minus. So this is now a Gaussian. So this is x squared. So the probability that this equals, so this is x0. probability that this equal x, let's say, we have a Gaussian, so this is x squared divided by sigma 2 sigma t. And sigma depends on gamma. You agree? The sigma we have calculated, which is this, depends on gamma. All right. So now what happened? Yeah, this is I wrote it in dimension 1. If it's dimension 3, you have here, actually we can write, yeah, I'll do dimension 1 because it can be different in all dimension. I don't want to start introducing a tensor for the noise, that you can have noise. So let me do it just dimension 1. It's not very hard. If you have 3 independent equations in 3 direction x, y, and z, then we have 3/2. And if the matrix of the noise is identity, then you just have put a 3 here, and that's it. Okay. So now let's start the thinking. Up to now, this is the boring calculation. What is the meaning now of gamma large? We can look at how these behave when gamma is large, right? So we should look at this when gamma is large. So what do you get when gamma is large? Well, I hope these formula are correct. I think they are. So it's 1 minus exponential gamma t divided by gamma. You agree? So t is t. It doesn't move. Q is q. So I think q we had a value. Yeah, what is the value of q? Q. So sigma t. So this is 2q. So I wrote gamma. So q is actually gamma kt divided by m, something like this, right? Okay. So now, q depends on gamma. So we get 2 divided by gamma. And here there is a constant. Let's write it kt divided by m, which is unimportant, but we'll write it anyway. Multiply by t minus 2 divided by gamma, 1 minus exponential minus gamma t. And now you said it was plus exponential, no, 1 minus exponential minus 2 gamma t divided by 2 gamma. So in principle, if gamma is large, this for t not 0, this is going to 0, right? This is the same. This is going to 0. This can drop. So in the first approximation, when gamma is large, this is like 2 kt divided by gamma m divided by t. So this is exactly 2d delta t, which is a classical diffusion tensor for the Brownian motion. So when t is large, so what happens if t is 0? If t is 0, for example, if you expand for small t, this is minus gamma t, so this is 1 minus 1, there is a gamma, and gamma goes. Then you don't have any more such a beautiful result. You see that if t is small enough, this approximation fails, which means that the convergence in probability, so now when gamma is large, this behaves like the same that is in here, except that sigma behave like this, which is exactly the diffusion, the probability distribution function for a pure diffusion process. You are with me? Which means that in the sense, these equations, this is called the Smoluchowski, 1914 or 1916. This is the Smoluchowski limit, that the Langevin equation, in a sense, converges to the Smoluchowski limit of the equation that has its name. Except, so this is for t, basically big enough. Gamma t should be something larger than 1 over gamma. Otherwise, it is not correct. And this is what is usually forgotten in many applications. Because this is something to remember when you do chemical reaction. And if you use the classical framework, that is x dot equals your potential well. Suppose you have a potential well, you have a particle, and you have a parabolic potential well. This is the plane. It comes here and enters into this domain. So this is modeled as x dot minus this interaction potential plus 2d square root of 2d w dot divided by gamma. So I divided, so I take the Smolokhovsky limit, which is written somewhere. Yeah, it's here. You divide everything by gamma. So you get force divided by gamma. This is the approximation. Now, of course, the question is that when the particle escape, what is the meaning of escape? Escape is when you are in here. You're at the boundary. So what is the next move to be done? Either the particle goes away, or it can go back. And in the simulation, you do this, but it can come back inside and outside an infinite number of times. It goes back and come back. It goes back, you wait some time. So this is completely artificial. This is artificial. This is due to the fact that here the approximation is not anymore correct. So when you go outside from the well, if you have for a certain time a ballistic propulsion, because this is the ballistic, you have a velocity v0, then you move away and then you don't necessarily come back. All right, so that's why I think it's important to think about it for any type of simulation and to see what is the limit of the model you are using. And it is important because we need to model this type of process. Okay, so this is called the Smolokhovsky limit. This is called the Smolokhovsky limit. And so we have shown that the probability density function, P, let's call it gamma, converges to P of a pure diffusion process as gamma goes to infinity. And for T, let's say, larger than a certain constant. This is pure diffusion. So this is, convergence in terms of function. So you can have any good space, L2, maybe more than L2 here. If you have outside this constant, we can have very strong convergence. Okay, so this is the what I wanted to say about this limit.